Let's talk about polar molecules for a minute. If I take chlorine and bond it to carbon, and I've got my hydrogens like this, if you look at the electronegativity, it becomes pretty clear that carbon around 2.5 and chlorine around 3, that electrons are going to want to hover around chlorine. We should understand polarity pretty well at this point. So this molecule will have an electron cloud, something like a peanut like that, and you'll see more positive over here and more negative over here. That's really important to understand. If I do it the other way around, let's say I've got a lithium and I've got a carbon. Well, lithium's electronegativity is far lower than carbon, so you're going to see that charge this way like that. Well, lithium's kind of small, so it's probably going to look, the cloud's going to look more like this. That's my guess. So here's my positive side and here's my negative side. And what can I do with that information? Carbon is the source of all organic chemistry, right? So just remember this rule. When carbon is bonded to something organic, like chlorine, carbon will always be the cation, the positive. But when it's bonded to a metal, carbon will act as the negative, because it's all in relativity, right? So when we're looking at molecules, pay attention to this. So now let's look at all the functional groups we're going to play with and see how similarly we can predict this kind of thing. We can make methanol. There's my meth. There's my anol. Well, positive, negative. So you're going to draw it like this, a little positive to negative arrow pointing towards the alcohol. Notice that the carbon is acting as the positive end of that action. Alcohol, pretty basic. What about something like an alkyl halide? Carbon to chlorine, positive to negative. Negative there, positive there. So it looks exactly the same. What about an amino group? Remember, we're learning how to play with Legos here. Each one of these is a different type of Lego block. So an amino group, NH2 like that. Again, we get a positive and a negative. So you're going to see the electron cloud pointing its electrons toward the functional group that carbon is attaching to. Another Lego that we like to play with are ethers, where there's an oxygen that is bonded on each side by carbons, and then who knows what's off here, hydrogens probably. Oxygen's extremely electronegative, so you're going to see the negative cloud here. So it'll look something like, if I want to draw this electron cloud, going to see something like this action here. We could draw thiols. That's carbon attached to a sulfur. And we'll put a hydrogen on it. That's a thiol group. It's just carbon sulfur. Again, positive to negative. We can draw nitriles. Carbon triple bonded to a nitrogen like this, and it's off bonded to something else over there. Guess what? Positive to negative. Again, because it's an organic. Now, what if I take a look at something like carbon to magnesium bromide? That's a common thing in organic chemistry. Well, remember, magnesium is a metal, so it's going to go this direction. Carbon has higher electronegativity than metals do, so it's going to be reversed for something like magnesium. This is just the kind of thing you need to get a natural intuition for so that you can play around with it. How about just a carbonyl group, like a double bonded oxygen like this? Well, of course, that's positive to negative here. So I'm hoping you're starting to get an idea of what this looks like. What about an ester? Let's do an ester. We have a double bonded O here and a single bonded O over here and something off that way. You can bet your ripe potatoes that this is going to be going in this direction. So whatever this cloud looks like, you got your minuses with the oxygens and a positive at the carbon. Okay, I've drawn a methanol for you here. Can you see it? There's a methyl group and an anol group, the alcohol here. It's going to be polarity how? Well, carbon's going to be more positive than oxygen, so you expect something like that. But now what I'm going to do is I'm going to add an acid to this scenario. Okay, I'm going to add an acid to the equation, and acids provide protons. So here's my hydrogen. I'm going to protonate this oxygen here. Oxygen has 6 local electrons to begin with, right? Has a neutral formal charge, but once I've protonated it, let's bring this over here and look at how that's changed. This double bond group here, double electron group here is going to disappear because it's bonded now to a hydrogen. And the problem with that is oxygen now has a formal charge of only -5 to its +6. So this is a +1 formal charge on oxygen. Oxygen doesn't like that. Oxygen does not like having a positive formal charge, so it's going to punish its neighbor over here, carbon. It really does. That's really what happens. So you may see the dipole look like this from original methanol, but when I put it in acid, now it's going to look like this. It's going to become intensified. Oxygen is going to pull electrons from its neighbors as hard as it possibly can to stay in its cloud as best it possibly can to help compensate for this horrible offense of having added a proton to where it wants more electrons instead. So you go from a dipole that might look like this. When you put it in acid, now it's like this. And when you have this kind of a dipole, well, your molecule becomes open to manipulation. This carbon is very close to getting torn off entirely. This oxygen is like, just give me what you've got. Like it's holding a knife to carbon's throat. And it's like, do you really want to be with me? Do you really want to be with me? It's an abusive relationship at this point. Let's springboard that idea with the difference between polarity and polarizability. Polarity is a permanent thing. Polarity is something inside the molecule. That's the dipole. That tells you how strong this water molecule's dipole moment is. If you look at this molecule, of course, you're going to get a big minus in here. That jelly bean's going to have positive charges over where the hydrogens are. Huge difference in electronegativity. That's polarity. But polarizability is about how easily the field of electrons around the nucleus is distorted by electric fields around you. So if I take something like a chlorine, kind of on the small side for the halogen group, right? It has a couple of energy levels and then some electrons out here. Of course, it's not the shape, but we're just keeping it easy. If I bring some big negatively charged field nearby, this is going to kind of bend in a little bit to kind of move away from that. You see what I mean? But if I take an iodine, let's make some room here. Let's make some space. Let's get rid of this chlorine. If I take an iodine, I'm going to zoom out on the iodine. He's got a lot of energy levels, huge radius, and then he's got electrons floating around out here. They are much weaker on the pull to the nucleus. It's too many energy levels away. It's too far, even at the number of protons in the center there. These are very weak. So if I bring like a negatively charged field here, it's going to really bend away like this. That is polarizability. So you might picture something like chlorine, where maybe it kind of bubbles a little bit when you bring a negative field nearby, but iodine is going to like flatten out. See if I can make a more pronounced version of it like this. If I bring this negative tip here to it, I go to touch it with my finger. So polarizability, you can almost think about it as how squishy is this electron field when I bring it near a positive or negatively charged space. The easiest way to think about it is that when you go down groups in the periodic table, like right underneath oxygen on the periodic table is sulfur, and right underneath carbon is silicon. These higher energy level, larger atoms are going to be more polarizable than their smaller predecessors. Now let's think about why it matters. Well, because unlike charges attract, the fundamental characteristic for all polar organic reactions is that electron-rich sites want to react with electron-poor sites because relatively they have a positive and negative between them. So bonds are made when electron-rich atoms donate electrons to electron-poor atoms. It's just like plus and minus, but everything is on a relative scale, so a minus compared to a minus minus is actually a plus. You see what I mean? Let's take something that we're going to call an electrophile. Electro means electron, phile means in love with. This A plus loves electrons because it doesn't have enough. So this is our electron poor side of things. And over here, we're going to have a nucleophile, which has too many electrons. It's electron rich. That's a nucleophile. It's electron rich. Why do we call it a nucleophile? Well, if you have too many electrons, you're going to be interested in positively charged items. So he's going to want to attack the nucleus of something that's charged. They love nuclei. They're looking for positives to pass off a little of their excess negative to, see if they can get it to work out. So we will draw this double arrow as these lone pair electrons attack this positively charged electrophile. So again, electrophile too much positive. Nucleophile, too much negative in some way. And one other thing to note is this double arrow here. You could draw a single arrow like this or a single arrow like this. These half arrows are when a single electron moves. This double-headed arrow, the normal arrow we usually draw, that's a lone pair of electrons attacking. So what you're going to end up with here is an A bonded to a B. The two electrons that were here are now forming this sigma bond between A and B. This is very similar to the Lewis acids and bases video. And if you watch that video, by the way, good on you, because you need to know that stuff to survive going forward. But Lewis bases are electron donors. They give their electrons to Lewis acids, who are electron acceptors. So an electrophile will often be seen as a Lewis acid, and a nucleophile will often be seen as a Lewis base. It's electron-oriented, but Lewis acids and bases, and acids and bases in general, are chemistry general terms. Electrophile and nucleophile are organic chemistry oriented terms. This is about carbon bonding. This is about forming organic molecules. So you'll see this terminology used in your OChem class. Let's look at an example. Okay, let's look at NO2 plus. Is this going to be an electrophile or a nucleophile? Especially considering the fact that there's oxygens here that are going to be harping for some help. So this is going to be an electrophile. It loves new electrons coming in. What's the structure for NO2? If you want to come up with the right structure, you have to make sure you sign it correctly. So nitrogen's going to have 5 valence electrons, and oxygen has 6 times 2. I was thinking about the number 12. 6 times 2 gives me 12, and 5 is 17. But then we have to take one of those electrons away because this is a +1 ion. So we have 16 electrons to play with. Let's keep that in mind. So we're going to have NO2. 4 electrons have been taken with these 2 sigma bonds here. So that would give us 12. So we could put 3 lone pairs on each one of these oxygens like that. But that uses them all up. And nitrogen typically has 5 valence electrons, so this would have a +3 formal charge from just these 2 electrons, those halves of the sigma bond. That's not going to happen. That is just not going to happen. So let's back up a little bit, and maybe we'll try some double bonds like this. And maybe it'll end up being a resonance structure of 1 double, 1 single. We'll see. This is 2, 4, 6, 8 electrons gone, so we have 8 left. This looks like it's going to work out, actually, because I can put electrons like this. And that's all 16 right there. So what would our formal charge on oxygen be here? 2, 4, 5, 6. So this is a neutral oxygen. This is a neutral oxygen. Nitrogen likes to have 5 electrons, 0 formal charge. This is a +1 on the nitrogen here. And that makes sense because oxygen, being so electronegative, is going to be pulling pretty hard on the electrons. So I think if you're going to find a plus, you're going to find it at the central atom, which can best handle it, and the lower electronegativity nitrogen is going to, this is how it's going to work out. So this is where my plus charge is on this nitrogen here. Now if I bring on an electrophile, a nucleophile like cyanide here. Now this is Cn minus. Carbon has 4 valence electrons and nitrogen has 5. This minus charge means there's 1 more. So we have 10 electrons to work with here. You see here's 2, 4, 6, 8, 10. So this is what that ion looks like. Let me just take the numbers out of the way to keep it clean in here. Okay, so this nucleophile is going to attack this electrophile here. And nitrogen is going to want to reach out and touch somebody, as they say, right? So we're going to get some kind of an interesting configuration. Let's see. So we're going to get nitrogen. Well, let's give it a little more space than that. Let's scroll down a little bit. Well, when this nucleophile attacks with this lone pair of electrons and wants to form a bond here, nitrogen already has an octet. It's going to have to let something go. So it's going to let one of those bonds go. So we'll say, it doesn't matter which one we want to say. Let's say this one stays the same, and this one doesn't. And this one here looks like this now. So this carbon, which was a -1, is now neutral. So he's much happier. He or she, it is much happier. And what we're going to see is over here, is where our -1 kind of ends up, because nitrogen needs to maintain an octet. You're not going to have 10 bonding electrons to nitrogen. It can't do that. It's got like 7 protons. So the octet rule is going to stand for nitrogen, which means it has to push things off. And what you see here is that a multi-step consequence has happened. This carbon has taken its lone pair and attacked this electrophile with it. And as a consequence, this double bond has to release and move on to this oxygen here. And of course, that could happen here also. Either one of these, they're equal, right? So this is actually a resonance structure. I could have easily drawn the double bond down here and the single bond up there. And that means that this general space here between the resonance structures is going to be where that -1 hangs out. This nitrogen still has a +1 formal charge. If you notice, it's locally still only 4 electrons, but it has an octet, so he's not that angry about it. That's really interesting to me, because you'll notice that cyanide got to fix that extra -1 that was on it. Now it's neutral. It doesn't have that -1 anymore. It kicked that minus over to the nitrogen, who then kicked it over to the oxygen. Nitrogen started as a +1 and it's ending as a +1. And now it has a couple sigma bonds instead of a couple pi bonds, but its formal charge stayed the same. So nitrogen really acted as an intermediary here for electrons to double jump over to the high electronegativity oxygen over there. And especially because there's 2 of them that are going to be able to share that electron between them, oxygen is so good at that. That's what it's for. That is what oxygen does. So if you're wondering where electrons went, if you're getting lost, they probably went to the oxygens. That's where they belong. And I thought that this was a great example for our introduction to nucleophiles and electrophiles. So there you go. If you have questions, just leave them in the comments. I'll try to answer them. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.